Okay, my name is Moakhkhrul and I am going to present you the use of microwave office for optimizing Infineon LNA and modules. Me and my colleague Andriy will present these things. So, before going to start the presentation, I want to say a little bit about the agenda. So, why we need to model these things? Previously, we didn't have enough urgency to model these things. So, for that we need to go a little bit brief history of these mobile phones, how from first generation to this fourth generation, then what are the challenges for this 4G LTE LNAs and 4G LTE Advanced technologies, and then how can we model our LTE MMIC LNAs and modules using microwave office, and how can we use these models for the application of this LTE Advanced technologies. And using these models, we will later on generate new circuits and automatically generate these technical reports for the customer use. So, let us start with this history of this mobile phones. So, you can see from this picture, first generation mobile phones, it was quite big and we can only use it for voice communication, no data communication, no SMS. Then in the year 1991 from Finland, this second generation started. Over there we have little bit of data communications in the range of 50 to 100 200 kilobit per seconds. Later on in 2004 this 3G started, and there we can give more data speed in the range of Mbps, few Mbps. Then in the year of 2012, 11, 12, 13, in this period we have this 4G, and over there we have data rate of megabit per second, megabit per second to gigabit per second in this range. So, what we can actually see over there? So, you can see the complexity of this mobile phone structure is increasing over the time period, and at the same time if you see the life cycle of these mobile phones, that means for the time period for a new mobile phone to come in the market. So, initially maybe we have 2 to 3 years of time. On the other hand, in the latest mobile phones we have only 5, 6 months, 8 months in this time period. So, we have more complexity, at the same time less time. So, that means we need to support or find new solutions very fast. So, from there the requirement of this modeling, precise modeling comes. So, let us have a look some features and challenges of this 4G LTE technologies. So, you can see the data rate is from like 300 megabit to 1 gigabit per second. So, in the coming mobile phones we will have this kind of speed. Initially we have analog communication in first generation, then this digital communication comes and the number of bands eventually increase. Initially we have like 1, 2, 3 bands. Now we have 44 LTE bands. So, that means previous time for the first second generations we need to handle only 1 or 2 frequencies, maybe 5 frequencies maximum. Now you have 44 carrier frequencies all around the world. So, to cover up these things we need to handle lot of things actually. Then come to this operation of these mobile phones. So, now this 4G LTE mobile phones not only cover this 4G technologies, it has some backward compatibility for second generation, third generation and fourth generation. So, they call it 5 more 13 bands operation. So, it can operate different bands and in different mode and different bands. Another new feature of this LTE Advanced technology is carrier aggregations. Carrier aggregations means that different carriers can operate together to enhance the data speed. So, the carrier is usually from 1.4 megahertz to 100 megahertz using these carrier aggregations, and from the 3GPP specifications the carrier aggregation 5 carrier component can be aggregated together to have maximum 100 megahertz bandwidth, and using this 100 megahertz bandwidth we can achieve 1 gigabit per second data speed. So, this will be coming in the maybe next 2-3 years in the market. Another new feature is this multi antenna technology. So, MIMO technology, then 2x2, 4x4 and 8x8. So, the most important things you can see what I already told, that the life cycle or the coming into the market of this mobile phone, it is now 6 months or less than 6 months. So, you can see it is very complex and the lifetime has reduced. So, let us have a look on how complex is this structure of this RF front end. So, on the corner there are two green lines boxes you can see. So, in the previous mobile phones we have only one antenna and only one path for TX for RX. Now, you have so many antennas and it is possible with MIMO also. So, the antenna will be much more. So, the complexity has increased, and you see these are the the red boxes, these are the products for Infineon, and we are going to use microwave office to model this LNAs. So, what is in these boxes? Looks like the amplifier in the boxes. So, there comes the requirement for this MMIC modelings. So, for this precise modeling we need to for this precise modeling actually we use two measurements. One is this S parameter measurements and one is gamma out measurements. They are actually separated, and from there we extract the data and combine these two files to get these touchstones or S parameter files with noise data. So, actually there are simple 4 steps to get this data. So, it starts with like some complex not complex, easy or simple PCB design with Rogers, because the if we use this FR4 boards here, then after 6 gigahertz the modeling is not that good. So, what we did here, we put some tricks that we can measure the straight lines and model it quite well. So, if you see over here, so we have just 2 straight lines to measure the S parameters and these things, and these straight lines are really easy to model. And for PCB characterization we use this open, short and through circuit boards, so that we can, when we are using this port de-embedding, we can use all these 3 datas all together. And in the, after that we measure the device in this PCB boards, and in the end we do the port de-embedding to get the device data. So, let us have a look how does it looks like. So, this is the modeling of this PCB. So, we actually measure the device level S parameter till 10 gigahertz, and you can see the matching of this measurement and simulation. So, here in this red curve there are blue curve. So, this representing the angle or phase, and these other 2 lines they are representing the magnitude of the lines, that means S21 or you can show the loss. So, we are able to match these things till 10 gigahertz. Okay. So, till 10 gigahertz, at 10 gigahertz you can see we have roughly 5 degree of variation. So, this I should say this is quite good modeling. So, this is actually some fitting of this curve using different parameters, tuning different parameters. So, for port de-embedding actually we use this through model, and for verifying our data we use also this open and short data. So, you can see this from this open data, this is also quite matched. At 2 gigahertz we have roughly 2 or 3 degree variations, and all the LTE bands is in between from 700 megahertz to 3.8 gigahertz. So, if our circuit is matching quite well in this band, then we are quite happy with these things, but we were lucky that we had good matching till 10 gigahertz, and those are the models for these PCB boards. So, some more pictures for short and this through lines matching. So, you can see they are also quite matched. Okay. So, now we have this PCB modeling, then we measure the data, and now we need to do the port de-embedding. So, for port de-embedding we use this kind of structure. So, we have the measurement results with input transmission line and output transmission line. To get the data only for the device, we need to subtract the input transmission line and output transmission line, and we use this neg block to subtract this thing. So inside this block we have the model of this input transmission line, and outside in the left right side we have this output side transmission line. So after subtraction we get the device level S parameter and also the gamma of results. So there I plot a small picture. You can see this is before de-embedding, and after de-embedding they are quite close with these things, and these two curves, they are also before de-embedding and they are after de-embedding. So now we have the model of our device. Now the question is, how much valid is model? Is this, how much accurate is these things? To verify this thing we need to do some verifications. So the simplest verification we did, the board we have used, we measured the board, the noise figure of this board we measured, then we simulate the things. So the measurement and the simulation, they should agree all together to get this to agree with these things that they are quite okay. And this is the first verification. Second verification is that we make some application boards. So from the application board we measure the S parameter data and we measure the noise figure also, and we model these things using the file, using the data what we extracted some time ago. So you can see this is the verification board. So we put our matching inductor and capacitor here, and in the output side we don't need actually anything. So then we model our circuit. So these are the transmission line, this is the real capacitor, real inductor, and this is the SMA models, and then we check our circuits from simulation to measurement. So there I put some curves to show you that the matching. So you can see this gain curve. So from the simulation we got 12.7 dB, and from the measurement we got 13 dB, and from the data sheet this is also 13 dB. So they are quite close, and from the noise figure you can also see this thing. So the noise figure is little bit higher, 0.04, 0.05 dB, but this is quite acceptable. And the input return loss, if you see the Smith chart, so you can see they are quite well matched, and this is the output return loss. So now we have the modified model of our MMIC and MCM. So what we can do with these things? Now we can use this data to generate the application note and technical report to support the customers. So the customers who are using these things. So previously what we did, we actually prepared the board initially, then tune our circuit. Then we measure these things and prepare these documents. It takes quite a lot of time. Sometimes it takes like roughly 2 weeks of time. But you see, the mobile phone industry is moving so fast that we don't have 2 weeks time to support them. So they ask some solution and they give us 1 or 2 day time. So then we use this model to generate new circuits so that we can support our customers immediately. So these are the applications we can say. So at first we generate the circuits by simulation, and the second thing, we need to write the report, or we need to show the customer these are the performance. So to write the reports, this is also one hectic task. Like if we I will show the examples later on. If we use a quad band LNA, we have 4 bands operating together, and for that we need like roughly 60 pages of reports. So 60 pages of reports with tuning all these things, it takes roughly 2 weeks. So what we did actually, we generate these circuits in microwave office, and we use some scripting language to automatically generate the reports. So we created the database using this model for supporting all the 44 LTE LNA bands. So actually we have all the solutions now, you can say, the existing LTE bands and the bands which are coming. So I will show you the database later on. So once we have these things, then we go to this automatic report generation process. Maybe Andriy, you can explain this thing to them.
My name is Andriy Gordiyenko, and I supported the people in this project with solution for automatic report generation. As you got from Shago, that the life cycle of product is very short now, and we need to provide documentation in very short term. Therefore, to generate 60-page report, 2 weeks is not acceptable, and we needed some new solution for this. And we thought about automation of report generation and generation of all measurement inside of microwave office. So the microwave office offers very good possibilities, API, which can be used from Visual Studio or from internal script environment. And we decided to create some kind of interpreter language to drive the microwave office and generate scripts. So this is this is a text script, right? Which will drive microwave office and generate a lot of graphs, which then will be automatically put into the Microsoft Word document. With such a solution, we can reduce our documentation generation time from 2 weeks to just maybe half a day, including the creation of a script. And we have very high reuse factor because this script can be parameterized. It supports variables, it supports hierarchy, so it can include in the top part of script can include some specific application stuff, and bottom part can include some typical stuff for all application nodes. So so we created a program in Visual Studio which drives the microwave office, creates here graphs, then it takes these graphs and copies to the Microsoft Word project. I will tell a bit about the user interface. So this is a simple Visual Studio program. It's Windows program, and it has few functions. First function is create graphs. This means that if we press this button, we got a menu to select a text file with a script. Then the script will be imported, and microwave office graphs will be generated. Afterwards, after it's finished, we need to use the next button and copy all these graphs to the Microsoft, to Microsoft Word document, which was prepared, some standard document. We have also possibility to debug program to see the flow step by step, to be able to debug some during the script development time. So this is example of few commands inside of a script. So this is the format of commands is pretty simple, straightforward. That you write like plot graph, for instance. You write device name, you write legend name, and big part is done in the down script because plot graph, in effect, it's a macro which knows which scaling should be used. It knows which steps, sub-steps, markers should be set. And this command will generate such a graph. And the next command, like add picture, input, and then the capture of a graph in microwave office will put this graph to the Microsoft Office document, to the Microsoft Word. So there is also automation for the band number. This means that if you need to have different frequency band, you just need to put the number of a band. It will be generated automatically. Also the capture, generated from name of the device, and you do not need to write every time the name of the graph inside of Microsoft Word. So then I think that Shago will present a live demo.
So before going to the demonstration, so what we are going to demo? So this is a quad band LNA we are using for demonstration. So it has 4 different inputs. So LNA 1, LNA 2, LNA 3, LNA 4, and there are 4 different outputs. So they are actually working for 4 different bands. Okay, so let's go for some. So as I told you that I will show you the database. So this in the left side you can see there we have all the solutions for all the LTE bands using these models. So whatever the customer wants, now we can support using this thing. So you can see it's quite big actually, 4 into 44, something like this much of circuits over there. Okay, so from there if we look at the script, so there are some script here, you can see. So, from there we are using it for band 41, band 26, band 12 and for band 1. So, let us use this one. So, we have seen this thing. So, let us go to this create graphs and we go to this script and we call this script. Okay. Let us open it once again. Create graphs. Okay. So, you can see all the graphs are erased and it is creating all the graphs. So, when it is running, I show you the report actually what we generated manually. So, you can see this is a 56 page of report and you can see the number, the curves are over there and you can see there are in this report there are roughly 60 pictures. So, plotting them by hand in the microwave office, then it copying it in the Word, this is quite hectic task. So, okay. Let's wait some time. It's generating the graphs. It takes like 2-3 minutes of time to cover everything. So, you can see this is already generated. So, this is some standard template actually we are using and it actually copying all the pictures, but we need to do some manual manipulation to make it look nice, something like this. So, here you can see we place it everything quite nicely, but we need to do it manual, like manipulation little bit so that it looks nice and update the things. So, altogether maybe we can save couple of days in generating one application notes.
The presented data now, is it measured or?
No, this is the simulated results and you can see this one, this is the measured one. So, actually what I try to do, so this is the this PDF, this is the measurement one. It takes roughly for 2 weeks of time to prepare, but we immediately with this simulated model device model, we immediately can prepare this application note or technical report. So, actually we are saving a lot of times in this way. So, after that if the customer are looking for the measurement results, okay, we want the measurement results, then we have the circuit, everything, just we can prepare these things and measure these things and give it to the customers. So, now what actually this, okay, so now we have the model generation, now we have this documentations, then we put everything inside this online library and the customer can access this models, S parameter files and also these documents. And this is all about the presentation and what actually we gain. So, from this modeling we get that good agreement between simulation and measurement results. And okay, if I go to end, and we can save time like roughly 2 weeks to, like he said, half a day or even one hour, something like this. Okay, then I think I can finish my presentation. Okay, thank you very much.